Hey everybody, we are looking at the answer key for this practice quest for Unit 7 differential equations. The real test might be a little bit longer. This one seems to go pretty quickly, but we'll see when we get to the end of this video how long it took me. Verify that something is a solution to a differential equation. You could be asked for a differential equation that is more difficult than this, in which case you've got really multiple stages to plug in, and it's really impossible to solve by separating. However, this one, because it is just a simple dy dx, and we have just x and y like this, I would say that definitely the fastest way to go is to just write it as a differential equation and then separate those variables. So you can see I've done that here. I've replaced y prime with dy dx. I've divided by y squared. This lines up very nicely so that we've got our variables diagonally opposite like this. So then I can separate them out and I can integrate. When I integrate, I get 1/3 y cubed equals 1/2 x squared plus c. Of course, there could be constants on both sides, but I just move them over. I then want to clear the fractions, looking at my answers up here, so I'm going to use that as a sort of a guide. Multiply by 6 will clear those fractions, and then as you compare each one of these, I think you'll agree that the only one with the right coefficients is a, and if I just make c, in this case, -6, and I move the 2i over and the 6 back across, I get exactly that. So that's, I hope, straightforward. Number 2, the amount of carbon, radioactive carbon in a charcoal sample. This is how they date, shipwrecks and things like that with carbon-14 dating. The half-life of carbon-14 is about 5,700 years. So we're going to use that fact to solve for K and come up with that constant, okay? The original setup, though, it's telling you really what this type of problem is when it says that the sample decreases at a rate proportional to the amount of carbon. Come back to this is sort of our basic population or radioactive, our exponential growth or exponential decay template. And when we solve this, remember, again, by separating the variables and integrating, which you do not need to know each time. Once you've memorized this little trick, you can just write it as that, P of t, population, is just some initial population, then e to the RT. So that's our basic startup. What we need to do then is say, well, okay, we'll have, this is 100% of the some amount of carbon. You could use, 10 grams or something like that, but it's better just to think of it in terms of a percent. We know that after some amount of time, 5,730 years, we'll have 50% of it left. So this is my true mathematical statement with only one unknown. How do I solve for this? Well, I divide both sides by 100. I'll get 1/2. And then that will be equal to e to the k times 5,700. Well, e to something, I take the ln of both sides, and then that will be leaving me with, and I have a minus in there. You don't really need a minus. I would just set it up with the k as being positive, because then we'll get k times 5,730. And you'll see then all I need to do is divide both sides by that 5,730. So which one of these is that? It looks to me like it's C right there, okay? On to number 3. For which of the following differential equations will a slope field show nothing but negative slopes in the fourth quadrant? Well, we know our signs. This is the fourth quadrant here. The only one of these that is going to give me negatives is this guy here, because the negative in the y will stay negative. The x squared is always going to be positive, and then subtracting 3 will always keep it negative. Hopefully that's fairly straightforward. This fourth one here, you definitely need a calculator, and you need to know that a velocity is the change in position with respect to time. So that's this little factoid down here, that the velocity is the change in position with respect to time. So this is then a differential equation right here. So I set up my little Euler's method chart where we're going to start at step 0, and if we're going 5 seconds and we're going to go from 2 to 12, that's 2 steps only, so that makes it easy. We're starting at time 2, and we're just going to arbitrarily say that it makes it easier to say we're at position 0, okay? And then I just do the math. I plug in 2 for t, and so 200 times the ln of 3 minus 2 is going to give me, in this case, 217 when you put it into a calculator, 0.722, something like that. Well, now we've got the slope, with Euler's method, we've got some starting position, and now we know the slope, so we go out here 5 units, there we are at 5, from 2, actually, to get to 7, and I'll be at a new position. So I multiply the difference here, the delta x, times the slope to give me my resulting delta y, or in this case delta x. So I multiply that by 5, and I get 1088.61. Khan Academy is very good at kind of getting you organized with these charts. Then when time is at 7, then this is, if I started at 0, I've accumulated that much height, 1088.61. Now I put in 7 and I do the 200 ln of 8 minus 7, and I get 408.88. And again, the delta t is just 5, and my new change in the y is 2044.44, I think. Okay? And then all I do is I add that to this, so add that 2044.44, and I think I get the answer of 3133.1, something like that. So that looks like that's answer B. All right? In the home stretch here, no calculated needed. We're given a rumor spreading. This is going to be a logistic curve where nobody knows in the beginning. It grows exponentially, and then there's some carrying capacity, the number of kids at the camp. So remember, just like our radioactive decay, we start off with this, but when we have a logistic growth, we introduce this factor that's 1 minus, and then P over M, the carrying capacity. Well, I've rewritten that over here to be K times Y, the Y variable, and then Y over M. And then if you look at the original setup, we're just told that it's on a decimal proportion, so 99% would be 0.99. So that means our carrying capacity is 1. And if you look at this original, the 2 is out here, so that means our multiplier K there is 2. So we've got that. We always know that the rumor is going to be growing fastest when it's halfway to the maximum amount. So halfway to 1 is 1/2. When 50% of the population has heard the rumor, it's growing the fastest. If at time t equals 0, 10% of the people have heard the rumor, write an equation, write a logistic equation. So we need to, this is the logistic equation that you're supposed to know. We've derived it in class. We need to find that A naught, that coefficient right here, and that's always going to be the carrying capacity minus your starting amount divided by that starting amount. So in this case, it's 100% minus 10% divided by then 0.1 gives us 9. And we know that our K value is 2. So 1, again, this is the full carrying capacity, and then it's just 1 plus 9 e to the minus 2t. What is the time in exact terms when the rumor has been heard by 3/4 of the summer camp? So if I just fill in what I know and then work carefully to solve, I've got, I just kind of clear fractions, and I then subtract 1, and then I take the ln of both sides. I think you'll see that the answer is 3/2 ln of 3. That's the exact time. It's worth thinking about, well, what is that, hours or seconds? I think that since the ln of 3 is a little bit more than 1, and that's going to be 1.5, it seems to me like a small camp with a crazy good rumor is going to maybe be in hours rather than days. So I would probably guess that that's what we're talking about here. And finally, a slope field. Consider this differential equation. Note that it is separable. Construct an approximate slope field, which I've gone carefully and tried to do. See if you agree. Then part B is find a solution, which I've got going over here where I've separated those variables. Again, very important technique. And then I've integrated. I've introduced my constant. When I clear the 1/2, I've got a new constant. And I've solved then for y. And here's my y equation. And then I have an initial value that we've got that at when x is 0, it's 1/2. So I solve for my constant, and my constant turns out to be e. And so we then get the final variables in our equation. When I plug that in, try graphing on a calculator, it seems to make sense that it would be this kind of a solution based on our slope field there. So I'd encourage you to check that out. So there is your exact equation for that initial value problem. And then the domain is going to be that we cannot take the log of a 0 or a negative number. So I've solved backwards to find that. The range is going to be all real numbers. It's growing slowly on the right. I'm plunging on the left. And there you go. Good luck.